Okay, it's 2:02. I think we can get started. So hello everyone, welcome to ASIC seminar series. I'm John, the seminar coordinator. I will be today's moderator together with Ms. Kathy Medley, who is our communication specialist. Just so you know, then the seminar is being recorded, and the recording will be later published on our YouTube channel. So please feel free to check it out. And today, we are glad that our Associate Director, Ralph Ferrero, also joined us. So Ralph will be introducing the speaker before he gets started. So I think I'm going to turn this over to Ralph. Ralph, please go ahead.
I'm pleased to introduce our speaker, Dr. Ramaswamy. He's the director of NOAA's Geophysical Fluid Dynamics Lab in Princeton, and he's also faculty there at Princeton University. And Ram's one of the premier scientists in climate change, climate studies, and so we're going to hear his talk shortly. And he's a fellow of several professional societies, including AMS and AGU. Prior to his time at GFDL, he was at NCAR, and he's also served or continues to serve on several international panels associated with climate change. So look forward to his talk, and we'll turn it over to Ram.
Thank you very much, Ralph. And thank you also to John and also Cassandra for arranging the communications here. It's really a pleasure to be here speaking to you all. Wish it had been in person, but I think we have to do it virtually right now. And again, thanks for the opportunity to speak in this ASIC seminar series. I really look forward to the discussions with you and look forward to really hear your comments on some of the things that I'll be presenting here. So what I want to do today in terms of today's seminar is talk about radiative forcing, Earth's energy imbalance, and climate change. And I want to acknowledge here several of the people from GFDL who've really been doing the hard work in doing the science behind what I'm talking about. Ming, David Painter, Priyam Raghuraman, and Dan Schwarzkopf. Really appreciate their help. So the outline of my presentation today is to talk about the Earth's energy imbalance. And you'll see shortly that it's from the point of view of the observed satellite record and how we can understand it. What should we do to be able to unravel what it's telling us. And then I'm going to zoom in on the role of aerosols related to greenhouse gases in terms of the top of the atmosphere and surface radiative effects, and then how that actually goes to affect not just surface temperature but also precipitation. And I'm going to use observations together with 3 NOAA GFDL models developed over the years, 2004, 2011, 2019, each one of them used in various CMIP exercises and also in the IPCCs. And then finally, I'm going to end up with some implications of the monitoring of the Earth's energy budget and how we can actually go further than just monitoring towards quantification of contributions from various sources. So let me begin with the Earth's energy imbalance. And I'm going to primarily focus on what we're learning about greenhouse gas and aerosol signatures in the satellite observed radiation budget. And a lot of this work comes from my student, Priyam Raghuraman, his thesis, and a paper that he led in Nature's published last year. So why should we be concerned about an imbalance in the Earth's energy budget? Well, there are lots of things that happen because of the imbalance. Affects basically all climate parameters, whether it's atmospheric and surface temperature, whether it's a hydrologic cycle. Then after that, you start to look at the extremes, and then also the cryosphere, glaciers, sea ice, and also ocean heat content. So there's a lot of things which are symptoms of an imbalanced Earth. So we want to understand what the imbalance is and what are the causes of the imbalance. So one of the things that's really happened very beautifully in recent years are these 20-year and continuing record of the radiation budget monitored from top of the atmosphere by satellites. And basically, satellites are registering the energy going into the Earth and the energy coming out of the Earth through reflected radiation and outgoing long-wave radiation. And this is now the balance. In the balance, of course, you want the energy in to be the same as energy out. But we are noticing now that over the industrial era, there's been an increasing imbalance, first pointed out by Jim Hansen, and it's continuing. And what's different about the last 20 years is there's been a continuous record of this from observations. So you don't have to rely on models. You actually have the observations to tell you what is happening. And what is happening is, so this is you can see the cartoon of the incoming radiation, which is basically solar radiation minus that reflected. And then you have the outgoing long-wave radiation, and together these two are the components that you are tracking. So what is happening? So in the last 2 decades, and you see here the satellite observed measurements, and you see a distinct upward trend taken over those 20 years of about 0.4 watts per square meter per decade. And the so there'll be a lot of studies on this already. So it's actually a very well documented result from the satellite measurements that there's an upward trend in the Earth's energy imbalance. So it's kind of accelerating. So why is it increasing? And so there are lots of reasons why you would expect an imbalance. One is just internal variability of the system. It is a nonlinear system. There are oscillations. So what you could be looking at is internal variability. Another one is the effective radiative forcing on the top left you see, which is the forcing by climate agents like CO2, like aerosols. And then there's a feedback on the right-hand picture on the right-hand side. And so the feedback, the forcing, and internal variability are all contributing to the energy imbalance. And dissecting this further, what we've done is look at it in the form of an equation, where on the left-hand side is a rate of change of the imbalance. So this is like a change with time, so basically acceleration. And then you have internal variability, denoted by this epsilon. And then you have the delta ERF, which is the effective radiative forcing. And then the lambda delta TS, which is kind of response due to the long-term feedbacks in the system. So what Priyam and we did was we went about trying to calculate each one of these terms using the best available models and the just available results, period. So for the internal variability, for example, we ran a lot of control simulations from our own models, there's the NOAA GFDL models, but also the controls which are archived in the CMF6. And then we did several other runs. So basically, there were 48 models, about 1,400 realizations. Because, the Earth's course through time is sub one variant. You want to know what are the possible variations that occur, because that kind of helps you to map the extent of the internal variability. So that's how we mapped out the internal variability. And then in terms of the feedback of the system, we had the atmospheric model with prescribed SSTs and CI. So basically that is giving you under fixed forcing, the
Dr. Ram, I think we lost you. He just
plus the forcing.
Dr. Ram, can you hear me?
Yeah.
We lost you for about 10 seconds there, just to let you know. So maybe.
Oh, was it on this slide? Can you see the slides?
Yeah, but we couldn't see the slides for a second. I think we were on this slide. Is that correct, everybody?
Right.
Okay.
Yeah, good
you can
now.
see the slides, right?
Yes, we can see the slides now.
Okay, so this is a slide with the equation, right? You see that?
Yep, the methodology slide.
Yep. Okay, correct. All right. So the term on ERF is the effective radiative forcing, and that's obtained by looking at the atmospheric model version of the coupled model, forcing it with the prescribed SSTs and CIs, plus the forcings as they vary with time, minus this AM4 PSST, which is a response. So that effectively gives you the forcing over this 2 decades period. So that is how we evaluated these 3 terms. And I'm advancing the slide, and if you can't see the slide, let me know. The left side now that, sorry, the left side is the delta EEI trends in watts per square meter per decade. And what you see in the bar is the observed value. And this, by the way, the Ceres satellite that observed this. And then the internal variability from various kinds of runs is depicted by these lot of crosses. Each side actually, they are overlapping each other. But you can see the internal variability cannot explain this trend that has been obtained. The internal variability is, there is variability, but it is not of a sufficient strength to be able to replicate the observed value. So, and then, on the right-hand side, you see, for example, a control run from the couple model. And if you look at 20-year segments in this, there is actually no trend. I mean, there are lots of variations and amplitude varies, but you're not seeing the trend that is in the observed. Now, what does explain is the anthropogenic forcing and feedback. They are both needed to yield the observed what I call the energy imbalance trend. And here again, you see the original curve, the observed, which is in sort of black line, and then the straight line through that, that's a sort of dashed black line. Now, if you did only the calculation without the forcings, you get the blue line. So that actually is not giving you the right picture. In fact, it's a trend which is going in the opposite direction. Only if you include the forcings, you get this orange line, which starts to come close to the actual observed trend line. Now, dissecting this net energy into its components, basically short wave and long wave, what we see is if you look at the reflected sun, the change in the reflected sunlight, then again the observed is actually seeing a decrease. That's the black line here. And now you see that the orange line is actually starting to come mimic better the trend in the reflected sunlight. And it's a decrease actually. So when you see the decrease, what you get is, and of course, because you're working with a model, you can do these for individual forcings. So all forcing is, of course, the result that you are going to use to explain the net result of the observations. But you can do greenhouse gas only, you can do aerosol only. You can see that aerosol has kind of really dominated the show. It's actually a decrease. Basically, it's telling you that aerosols have been going out of the atmosphere. And that's why you get this decrease. Negative sign, by the way, positive sign means energy into the system. Negative sign means energy out of the system. So there's been a decrease in the reflected sunlight, which means really an increase in the system's energy. And then if you look across at the various belts, so you see the global, and the global observed is given here, but in terms of decrease in sunlight. The best that the model can do is actually this orange line. So it doesn't really come all that close. There's still a lot of gaps to be desired, to be filled. Internal variability is given by this, and then without the forcings, you get this blue line. And so you can look across at the various regions. One interesting region is the northern extratropics, where in the model, the decrease has been largest of all the other latitude zones considered. And it actually matches the observed in that region pretty well. And again, there's a difference between the observed, between the runs with the forcing and without the forcing, so that you need this change in the forcing to actually explain this decrease in reflected sunlight over this period. And looking at the long wave, there's been a small increase in the outgoing long radiation, which is depicted on the left-hand side. And here, the major portion is that the increase in greenhouse gases actually reduces the emission, but the feedbacks increase the emission because a warmer planet emits more. So it's a compensation between the two. And here, most of the changes are explained by the greenhouse gas changes. So we have a good picture of what, at least conceptually, the changes in the EEI are arising due to. Now let me change gears and talk about the more kind of bigger picture here. First, interestingly enough, the results from our calculations show that the forcing over this 20-year period has been half a watt per square meter. Now that's over 20 years. If you consider sort of this is IPCC AR6 computed or assessed forcing of total anthropogenic forcing over the period. it's about 2.8 watts per square meter, 2.7 watts per square meter. So 0.5 out of the 2.7 is a hefty increase over just the last 20 years. And if you consider just last 50 years, it's an even greater contribution. The thing to note in this diagram also is the fact that the greenhouse gases form one pretty huge chunk of the forcing, and that's positive. And then you have the aerosols consisting of both aerosol radiation as well as aerosol cloud interactions, forming a big chunk of the negative forcing. So this is basically going to be my thrust of my rest of my talk, that you're seeing in the system a big offset effect between greenhouse gas, or let's say aerosol offsetting of greenhouse gases in a big way, because this negative values are compensating to some extent the large positive values due to greenhouse gases. And so you end up, with a result like this, but you also note that because of the large uncertainties in aerosol, you end up with a substantial uncertainty, which is not negligible in terms of the net forcing being uncertain to some extent. But that's caused not by greenhouse gases, but really by the aerosols. So the aerosols have become a bit of an enigma in the last 40, 50 years that people have been studying the effect of aerosols. There have been lots of observations, lots of modeling, and we are coming to realize that its uncertainties are greater than that of the greenhouse gases. And again, drawing from IPCC AR6, you see the model simulations sort of showing that this anthropogenic forcing is actually having an impact, because when you look at the observed temperature, which is sort of the black line here, and look at the various models, which is the sort of shading here, and you see the mean running through those model ensembles, you see the mean model ensemble is actually fitting the observed temperature anomalies, surface temperature anomalies, pretty well. And whereas if you had only natural forcings, you don't match that. So this is kind of why the total anthropogenic forcing that you saw in the previous diagram is actually a pretty good revelation of really what is driving the surface temperatures. And again, this is, as I'll go later on, to show that the total anthropogenic forcing is comprising of these two really important forcing agents, greenhouse gases and aerosols. Now, as I already mentioned, that the error bar on the aerosol radiative forcing estimates is pretty huge. And this is another depiction of that, which is based on Monte Carlo calculations of forcings, and this is from AR5, IPCC AR5. And you see the greenhouse gas forcing is positive, and the uncertainty is pretty small. So the spread that you see is rather small. Whereas the aerosols are negative forcing mostly. There's a small possibility that they could be positive, but really what the attribution studies are showing is that that's not really possible. And then you have a large negative forcing, but it is kind of spanned by a huge uncertainty estimate, much larger than for the greenhouse gases, so that the net is also uncertain by a large amount. So aerosols are compensating greenhouse gas in terms of forcing, but they also have a large uncertainty. And it's not difficult to understand where the uncertainty is coming from. This is all the sources of various kinds of aerosols. So aerosols are multiple. In greenhouse gases, you have maybe 4 or 5 items like CO2, methane, nitrous oxide, halocarbons. There are lots of halocarbons, but kind of as a group, they are sufficiently sufficiently similar in features. Whereas for the aerosols, you have all sorts of sources. The ones in red border indicate those are anthropogenic, and then the ones in blue are natural sources. And then, the ones in blue are indirect sources, like gases then converted to particles. And then the ones in green are natural sources, volcanoes and sea spray. And then there are a couple of ones which are both natural and anthropogenic, fires, which can be natural or anthropogenic, and dust raised from arid surfaces, which can be due to just aridity because of geographic and seismic forces, or it can be due to man's clearing of land. So you have several sources of aerosols, and you also have this additional complication with aerosols, that when they interact with clouds, either in clouds or above clouds or below clouds, they give rise to different features or different signs of the forcing even. So this is a picture, for a satellite picture of the biomass burning, the fires burning in Africa. and then the plumes coming out of it. And you see that over land, you can have sort of a decrease in planetary albedo when it comes to over cloud because they're absorbing aerosols. But those same aerosols can actually increase the planetary albedo over ocean. So you have this dichotomy of what aerosols can do when they interact in regions with clouds. And that adds to the uncertainty, which is indicated by the bar that you saw earlier. So now let me go to the forcing and response issues involving greenhouse gas and aerosols. And I'm going to use the CM4 model for this part of the talk. So I kind of want to first mention that aerosols, we already said, are very uncertain in terms of estimates. And these are three estimates about aerosol forcing in the GFDL models going back to 2005, 2011, and then the recent one, 2018. And they all vary in terms of forcings. The first one had no indirect effect, which is the aerosol cloud interaction. So it was a very small negative forcing. And this, the model that we had in the 2011 had a pretty large forcing, which now we think was maybe too much in terms of magnitude. And then this is the latest aerosol forcing, which is somewhat actually matches, in fact, what AR6 assessed. And the other thing about aerosols, which I'll come to later on, is, and if you just concentrate on the blue and the purple shades here, this is the top of the atmosphere forcing, and this is a surface forcing, which is much larger than what occurs on top of the atmosphere. So this is sort of another thing to note as we go along in this talk. So in terms of the latest model from GFDL, again with the model you can run pretending as if the system was driven only by greenhouse gases, or you can pretend the system was driven only by aerosols. So you can do all these numerical experiments. So if you had only greenhouse gases, that's what the surface temperature change would look like over the past 150, between 1850 and now. If you had only tropospheric aerosols, then because of negative forcing, you see a decrease in temperature. And there are other forcings taken in between. And the observed is this black line. So clearly, the observed black line does not match that for greenhouse gases. So it means that there was some kind of an offset, which is basically mainly provided by the tropospheric aerosols. There is some from other sources, but mainly tropospheric aerosols. And if you see in terms of magnitude of the offset, greenhouse gases caused a 1.5 degree change over this period. Aerosols are minus 0.5 degrees. So the net is about 1 degree. So it's about a 1/3 compensation in terms of magnitude. That's in terms of surface temperature. When you look at precipitation, it's a little bit different story. Again, we know from very good theoretical and numerical calculations from the past that greenhouse gases tend to increase the vigor of the hydrologic cycle and therefore increase precipitation. And aerosols, again, because of their forcing, they actually decrease it. But in this case, and again, in this case, the black line here is an estimate of precipitation from NOAA precip reconstruction data. Now, in this case, the change over this period is one where the aerosol has nearly completely offset the greenhouse gas effect in terms of global mean. And this is indicated in watts per square meter, but you can see that it's almost totally compensated. And just to kind of do further analysis, I'm going to resort to another model that we did, which was an older model, the 2011 model, which, if you remember, had very large forcing. So you got to scale it down in terms of comparing to what would be kind of more realistic forcing, but nevertheless shows the physical effect. So first of all, the precipitation change in the 20th century, and I'm going to focus mostly on the global mean. And you see that there's a compensation. If you run with greenhouse gas only, and if you run with aerosol only, you get this almost complete compensation of the effects. And in fact, if you look at Asia, it's even more of a compensation in terms of the aerosol offset of greenhouse gases. Why does this come about? So to understand this, we have to look at the greenhouse gas and the aerosol separately. So in the greenhouse gas case, again, partitioning by the different components of the surface energy budget, net short wave, net long wave, latent heat, and sensible heat. And again, positive here means the surface is gaining heat, negative means the surface is losing heat. So in the case of well-mixed greenhouse gases, again, from well-known modeling of the past, greenhouse gases increase the longer radiation of the surface because of the trapping of radiation. There's more emission to the surface. Whereas in the case of, and then of course that is balanced by evaporation from the surface and more precipitation. So the surface tends to lose latent heat. In the case of the aerosols, you have different thing happening. The short wave is reduced at the surface, so you have a reduction in the short wave flux, and that has to be compensated by the increase in latent heat at the surface, which means actually a decrease in evaporation. So that's kind of why the previous diagram showed the loss in precipitation because of what the aerosols do or interact or respond to this shortwave radiation. So the net effect is what gives you this, where you have a shortwave effect, you have a long wave compensation effect, sorry, not compensation, you have a long wave driving effect from the greenhouse gases. So the net latent heat change is quite small. So that's why the precipitation is offset to a great degree in this earlier slide that I showed. All right, so this is GFDL models. So looking at some other models in terms of the global mean precipitation, this is from CMIP5 database. You see the greenhouse gases from various models, the greenhouse gas runs from various models showing an increase in precipitation. So that's pretty standard. There's some variation, but that's due to the forcings that may have been applied in the models. But basically, they're all showing an increase. Natural forcing don't show much changes except during the time of volcanic explosions, which are transient, and so the system as a whole over the century period doesn't really seem to have a trend. Now, when you do all forcing, which includes greenhouse gases and aerosols, you start to see this dip in most of the models in the 1960s to 1990s period, and showing a decrease in precipitation, which is to be contrasted with what you see for the greenhouse gas only runs. So aerosols causing decrease in precipitation is actually a pretty robust, at least qualitative phenomena occurring in all models. And again, if you look at the CMIP5 database in terms of the long wave and short wave fluxes at the surface, you see that you have the long wave surface. I'm missing something here. These are the all sky relative flux changes. This is the greenhouse gas case, where you see an increase in the long wave flux, practically no change in the short wave flux. And this is the changes when you have all forcing, and you see the greenhouse gas, of course, is the same as here, but the short wave flux, sorry, that's a long wave flux. The short wave flux is actually decreasing in all the models. So pretty consistent effect in all the models and conforming to fairly fundamental physical arguments. And in terms of observation, now this is where precipitation gets very tricky because the precipitation observations are just so difficult to grapple with, and it's tough to match the models with observations because of a lot of biases in precip. But this is one result which came out in AR6, where you see the GBAR result, which is the surface radiation anomaly. So you see sort of the dip over the 1980s to about 2000. And you see runs with aerosol in the models, again showing that dip. So pretty much, mean model ensemble actually gives you a fairly good result. I'm sorry, this is all forcing that you should look at, the red line, which is the ensemble mean from all the models. So it's a pretty good representation of the decrease in flux. And then bottom is the more interesting result, where it shows the precipitation anomalies from various data sets, and that's the black line, the dashed and the solid black line, showing again the decrease in precipitation in the northern hemisphere summer. And then you see the models. If you look at the all forcing, you see kind of a hint of a decrease in the models in terms of precip over this period. So there's a pretty strong argument now building up that and AR6 pretty much validates it, that there's been this really an offset by aerosols during at least the period over 1970s to about 1990s. Okay, so another thing the aerosols do, because of the way they are, most of them are in the northern hemisphere, so the perturbations are mostly in the northern hemisphere, but that northern hemisphere, southern hemisphere asymmetry causes the shift in ITCZ. And quite a few years ago, this was shown by Chung and Ramanathan about the shift in summer rainfall over the last half of the 20th century in the case of a lot of regions, not just one region. So Asian rainfall, the weakening Indian monsoon, the Sahelian drought, all of them where you do get a desiccation in the northern part of in the portions north of the equator, and then just south of the equator in the tropics, you get a increase in precip. And this is actually well explained by very simple model experiment. This was one that Yiming and I did several years ago using a model with a coupled to a mixed layer. And you see that this actually runs using the forcings up to present day. And for greenhouse gas, you see this dashed line, which is a pretty conventional result in terms of peaking in the tropics and then sort of very symmetrical about the equator. Whereas with aerosols, you get this sort of especially because aerosols are mostly in the northern hemisphere, you get this dip in precipitation just in the northern part of the tropics, and in the southern tropics you actually get an increase because of mass continuity and the change in the Hadley circulation. So this is something that is also seen in the later model. This is actually from the CM3 and CM4. You see kind of this very characteristic change in the precipitation, decrease in the south, decrease in north of the equator, increase in south of the equator. And greenhouse gas alone, which is the green lines here, cannot give that. It's a very unique feature of aerosols in northern hemisphere that this happens, this sort of change in the ITCZ, or the shift of the ITCZ to the south. And in terms of observations, there actually was a figure in the AR4, which is reproduced here, about the century scale zonal mean precipitation trend, and that's a black line here, which actually shows that characteristic change, which was actually not very well understood at that time. This is 2007. The observations showed this. The models were, excepting for a couple of models, none of the models really got it, although the mean model ensembles gave a hint about that. So it's something that is now, AR6 now actually has really built upon that, and now the aerosol influence is recognized very tacitly. Okay, so that was all the 20th century. What about the 21st century? So in the 21st century, what will happen to aerosols is depicted by this bottom panel. And these are the three models that GFDL has used, but you can see in all of them, there's a peak around 2000, and then they are decreasing because of scenarios. And I'll go to the temperature and precip in the next few slides. One of the things that would happen, when that happens, of course, is that aerosols are decreasing. We've already seen that from satellite data. Greenhouse gas is increasing. So the warming is going to increase. And what you see in terms of regional changes, so I'm actually going from global to regional in this figure, that at 1.5 degrees warming, 2 degrees warming, 4 degrees warming, you see how red the regions of the Earth get, especially the polar regions, because of amplification of the warming in the polar regions. So that is kind of something that is to be borne in mind now, that greenhouse gas are increasing and aerosols are decreasing. So this temperature increase in the 21st century is going to have to be watched out, because it might be accelerating because of the acceleration of the energy imbalance. And this is a result from CM4 for temperatures. And of course, we are in 2000, and the graph goes up to 2100. If you had greenhouse gas only, that's the purple line, which is the track you will take. And if you had aerosol only, that's the track you would take. And you see the decrease in aerosol causing sort of a reversal for the aerosol only runs. So that the net effect is this blue line. And you can see the blue line is, whereas here it's not very close to the purple line, it is getting closer and closer to the purple line, namely the greenhouse gas driven solution for temperatures. And the black line is the observed so far. So it goes only up to 2015. In terms of precipitation, again, the purple line is the greenhouse gas only run. Green line is the tropospheric aerosol only run. And you can see that around 2000 or 1980s, 2000, how much the compensation is by aerosols of the purple line. And the net result is given by the blue line. And the black and the dashed lines are two different constructions of precipitation. One is land only, which is the dashed line, and one is land plus ocean. I can sort of see that precipitation is a difficult field to contend with, but again, you see this decrease in precip occurring somewhere around the 80s and 90s, pretty unambiguous in the two data sets. They might be phase shifted. But again, I think the point of this figure is to show how the blue line is going to get to the purple line. And so a key question is the rapid reduction in the aerosol offset of greenhouse gases in the 21st century. How rapidly is it going to occur? If the aerosols are going to come out of the atmosphere, then it is going to occur at some point. But how rapidly? Because, well, let me get to that point a little later. So again, pooling together models that we've done, the 2011 model and the 2019 model, this is the sort of general picture. So in the beginning of the 20th century, you had some greenhouse gas influence. The forcing was not much, but aerosols were not that much either. You had a lot of internal variability also playing a role at that time. And then over this period when aerosols dominated, you actually have an effect which is aerosol is comparable to or even maybe greater than greenhouse gases. And then as you go to the latter part of the 21st century, the scenarios would predict that greenhouse gas is going to be the dominant enforcer of precipitation changes. In terms of understanding the precip changes in the 21st century, again, it's really a reversal of the theory that you have for the 20th century. Nearly with respect to 2000, the net short wave actually now increases because the aerosols have gone out of the atmosphere. The net long waves continue to increase because greenhouse gases are being added. So now you have the latent heat flux compensating for both these positive gains by the surface. So it's an increased loss of latent heat from the surface, which means more precipitation. So an acceleration of precipitation comes about because of just these two quantities exerting their effects in practically the same direction. And one of the consequences, again, from AR6, which spells out very clearly, is that as you get to the larger greenhouse gas forcings, you intensify some of these highs and lows in precip across the globe. This is sort of looking at regionality here, but you see the colors intensifying as you get to 4 degrees warming. And that is going to be something that the changes in precipitation will entail. It will not be an increase in precipitation everywhere. There are going to be places where it will continue to decrease. So that's kind of the sort of famous statement about wet get wetter and the dry get drier paradigm in terms of a solution for the planet, in terms of planetary solution that has more greenhouse gas dominated features. All right, so now finally I get to the final part of the talk, which is, monitoring of the Earth's energy budget. And we've taken this cue from really the rather seemingly good agreement that we can get between models and the observed satellite energy budget over the last 20 years. And the fact that you're able to see or discern aerosol decreases and greenhouse gas signatures on record makes us go maybe one step further on this. And that is, can we actually monitor the Earth's energy budget, continue to monitor the Earth's energy budget from the top of the atmosphere, of course, but including spectral characteristics and also monitoring, importantly, at the surface, because of the importance of what's going to happen at the surface between aerosols going out and greenhouse gas increasing. I'm going to kind of go back to a figure that one of my former students about 15 years ago did in terms of the spectral signatures. If you compare 2000s minus 1860s and then 2100 minus 1860. So basically assume that you had a satellite monitoring the spectrum of the Earth's radiation continuously from pre-industrial era, from 1860s. What you'd observe as a change is the blue line up to about, the red line is 2000 minus 1860. So the red line is showing you the changes occurred in different parts of the spectrum, and they're caused by different constituents. So there's a CO2 bands here, ozone here, and then methane, water vapor vibration, rotation, etc. So you can, and then if you go to the 2100, where the signal is going to get stronger, you'll see this big dip in the CO2 wings. And this is something that would be very, very interesting to monitor, just the spectral characteristics, in addition to the total energy that the Ceres satellite is measuring, because you can learn so many things about like how much the gases are increasing, which gas is increasing by how much, and so on. So this is an idea that was that's been there for some time, but in terms of attribution and in terms of understanding the budgets, it may be necessary to actually think about this again. And then I come to surface forcing. One of the most classic results in recent years has been this result from Feldman et al. In Nature in 2015, where they actually looked at the arm side, the DOE arm side Southern Great Plains record of the downward radiance. And by looking at model and calculation, they were able to infer that methane forcing is actually evident in the surface, just looking at the methane absorption band. And so they actually concluded that between between 2002 and 2007, it was actually not much, and then from 2007 to 2012, it has actually increased by so much watts per square meter per year. So this actually gives also an impetus to really measuring things at the surface, so like radiative balance at the surface, short wave, long wave, so they can actually clearly identify what it is that greenhouse gases and aerosols are doing. And so I'd like to conclude my talk with the 2 slides. First is that model simulations indicate that aerosols have offset the greenhouse gases in the 20th century. This is much more substantial for precipitation than surface temperature, and the largest effect is in the Asian monsoon region because of a lot of localized local aerosol effects. The predominantly northern hemisphere aerosols induce a southward ITCZ shift, and this is characteristically different from greenhouse gas effects on zonal precipitation. The satellite observation of the Earth's radiation budget over the past 2 decades has been really phenomenal. It has definitely indicated aerosol effect on top of the atmosphere budget has turned around. And past 20 years of record suggests that aerosol is decreasing, which has given rise to a major shift in the radiative imbalance, besides that for greenhouse gases. The recovery from aerosol effects in the 21st century shifts the global precipitation control increasingly to greenhouse gas dominated solution, which means increased hydrologic cycle vigor relative to the 20th century. Now, one caveat is that the statistical significance of precipitation trends is notoriously difficult. So comparing models with observations, unlike for temperature, is a little bit more challenging task. But the available data nevertheless suggests that greenhouse gas forcing influences have been offset to a significant extent in the 20th century because of the aerosol effects. And finally, in terms of just implications for Earth's energy budget in the 21st century, I would lay down this premise that monitoring of Earth's energy budget and the agents causing the perturbations is essential for understanding the processes and the rate at which warming and the change in precipitation would occur. Now, the TOA and surface measurements give rise to a facility for quantification of the thermodynamic and dynamic response of the climate system. And this includes the surface heat and water balance, which of course links to surface temperature and precipitation effects due to the different forcing agents. Why do I say that continuous energy budget measurements are critical at both TOA and surface? Well, you can do attribution. You can actually say about how much a change in the atmospheric composition of anything, long-lived greenhouse gas, short-lived greenhouse gas, aerosol, is actually contributing to changes in the energy budget. And then, of course, you can also monitor regional sources of perturbations, large emissions of aerosols, for example, in some place, or large emissions of methane from any place. And also this helps in terms of assessing how would be the rate of recovery to a balanced planetary energy state. How can we compute that? How can we quantify that? And I'd also offer that spectral measurements at the top of the atmosphere, together with state-of-the-art computations involving radiative transfer models, actually hold substantial promise for closing the loop on how you can match the atmospheric composition changes and plus other forcings like land use forcings too, and their impacts on the Earth's energy budget. So that's I think, a very optimistic outlook that we can have about how to monitor the changes in the energy budget, which of course then feeds on to changes in temperature, precipitation, other climate parameters, ocean heat uptake, and also of course gives clues to adaptation measures and also inputs into mitigation arguments. So with that, I'll like to end here, and I thank you very much for your attention, and thanks for inviting me to give this talk. I'd be happy to take questions now.
Thanks, Dr. Ram. If anyone has a question, you can go ahead and unmute yourself and ask it, or you can raise your hand and I'll call on you. If you don't have a microphone, you can type your question in the chat. I'll just read it out loud.
So if no other people, I will ask one very interesting summary of so many things. For the radiation imbalance, we observed in last decade, how long do you think this can be persistent? I just don't think, the Earth will certainly get warmer and then will emit more to compensate for it. So any model or any estimation how this trend will evolve over time?
Well, how this will evolve. So, I mean, obviously, greenhouse gases are going to increase. So you get initially the reduction in the flux because there's a trapping of radiation, but then you get the feedback effects where the Planck function starts to come into being, and then of course there's also cloud changes. So, but the net effect seems to be one of where initially the long wave flux reduces, but then it'll pick up because you have the long-term feedback, involving sea surface temperature changes. So I mean, the imbalance will continue to increase until the Earth is warming up, so that then the equilibrium is reached at a higher temperature. So that's when if let's say greenhouse gases were to stop today, then there's probably an equilibrium solution for that, which at a higher temperature, let's say 1.5 degrees. So that's kind of where things will, the energy, then you shouldn't be able to detect any changes anymore in the EEI.
Yeah, that's certainly likely to happen, I think.
But as long as the greenhouse gases keep increasing, then you're going to continue to get this imbalance in the EEI. I mean, and that the rate of change in EEI, whether it's keep going up or whether it flattens out, is actually going to be an indicator of whether the system is stabilizing or God forbid, destabilizing, where maybe there's a runaway effect, although that's very unlikely to happen. But it's something that's a good indicator. It's in fact, in many cases, we've been talking about it a long time in the IPCC assessments about radiative forcing. And the radiative forcing is actually a very good first indicator of what the impacts on climate are going to be, because it gives you directly this link to surface temperature. And even if it's just global mean, you know that if global mean is rising, a lot of regions are also warming up.
Dr. Lee, did that answer your question?
Yeah, very well. Thank you, Rob.
You're welcome, Zaki.
Okay, so we have a few text questions. So I'm just going to ask one. This is from Ralph Kahn. He said, really nice overview, Ram. I'm wondering how possible increases in aerosol amount due to increased fires, desertification in increased drought areas, etc., are treated in the model predictions.
Yeah, that's a good question. Thank you, Ralph, for asking that question. There are still uncertainties in the models. I mean, you can sort of say that, or you can tell that when I showed the picture of the decrease in sunlight, that it wasn't really matching the observation very well. The observed decrease in sunlight was actually much more than kind of what the model was saying. So we wonder whether some things have been very seriously neglected. One of them is dust. Dust is not treated as dust is treated as an aerosol which can be transported right now, but we are not very confident of how dust is represented in the models, especially the changes in dust loading with increased human activity, increased agricultural activity, increased aridity that might be happening because of the long-term climate change. So dust is poorly represented. Another thing we think is poorly represented is sea salt aerosols, particularly in the southern hemisphere, where there's a vast amount of oceans. You have a vast generation of sea salt aerosols, and we are not confident that that's being represented very well. And then, of course, fires. There are increasing number of fires. These are not necessarily simulated by the models. In fact, one wishes that one can do an interactive simulation where you can actually create fires in the model because of various conditions like the drying and then the warming in the summertime, and then those fires release a lot of aerosols, and then the model should be able to track those aerosols and see their effects. We don't do that job very well. I mean, at the best, models are doing a proxy kind of thing. That's not good enough, and so fires are again a source of uncertainty. Now the question is, how much would that alter the picture on aerosols? I think it would. There's definitely would be an alteration regionally, especially over I think land areas where these, and in the southern hemisphere oceans where these things are more uncertain than other places. In the global mean, perhaps not so great an effect, but regionally, a lot of effects. And of course, even if they have just regional effects, the connection between regional climate impacts and that feeding on to global climate cannot be ruled out. So there's a lot of things about aerosol that we still have to learn. It may be that they kind of have a greater, it may be that what models are doing today has a greater impact on temperatures and maybe a reasonable impact on surface temperature. But in things like hydrologic cycle and other quantities of interest in climate, perhaps not so well. That is still a route to be. I mean, that uncertainty bar you saw in the radiative forcing estimate, even coming up in AR6, that uncertainty bar is big. I think that indicates the state of affairs, that we still are struggling to nail down aerosols to the level where we've nailed down greenhouse gas forcings.
Thank you. And then Betsy Weatherhead had a question. Betsy, you can go ahead and ask.
Thanks, Ram. I think I speak for everyone in saying we so appreciate the way you present this work, in particular the way you make it clear where there's progress and where there are still challenges. My specific question for you is, often when you present observational data, not always, but often you just have it as a solid black line, kind of like here's our truth. And with precipitation and with water vapor, we understand how large the uncertainties are. What would be useful to you and your modeling colleagues in terms of having the uncertainties, the long-term trend uncertainties, quantified for you better? And just to let you know, Tapio Schneider and Dwayne Walliser and I are working on a JPL workshop on this topic. So truly, what you say now could influence where we can direct work towards. So as a modeler, what do you need in terms of measurement uncertainties of long-term data sets?
Yeah, I mean, that's an interesting question, Betsy. I know you've been working on this topic for so many years. You know, it would be good to, however it's done, it would be good to really get the quantification of the uncertainties. And maybe that's not a right word, quantification of the variability in precipitation. I think before we start doing linear trends, which I agree, I mean, that's zeroth order thing to do, but maybe not the first and second order things to do in terms of nailing precipitation accurately. Just like we do on temperature. I mean, there's been so much attention on surface temperature that now, you know, it's been kind of, you know, diced this way and that way, and we kind of can come to a consensus on what the changes are and what the variability is. But in terms of precipitation, that is still so much hanging in the air. I mean, we don't really have enough data. Oh, no, I said we don't have enough analysis, and maybe data too, to really challenge the models. I mean, the models are not really being challenged. I think there are a lot of surprises still to be had, particularly on precipitation extremes. You know, like frequency and can we explain the frequency? Is it all variability, for example? Is it all random? That is the kind of thing I think models not only should appreciate, but should like the challenge, because I think that's important, especially as we're looking at a quantity which is proving to be, you know, difficult to handle, but nevertheless, it's a very important quantity. I mean, the excess or deficit of precipitation, it means so much, you know, in many areas of the world, that it is important to get that. I mean, however, I don't know enough about observations to say how it should be done, but I think you are there, and I think you should get us that so that the models are challenged, and not only, you know, in terms of global means anymore. I think we have to get to the regional aspects, and where, you know, it's a more difficult task in terms of precipitation, but that's kind of where we have to go. And then on top of that, you know, not just look at the projections only, but actually look at predictions, where you're dealing with the initial value problem. Now, there's initial value is going to be forced by climate change, and that makes it even more interesting, I think, or even more daunting, depending on how you look at it. But we need really a good, healthy assessed data that reflects the variability as well as the trend from from all the precipitation analysis, because the models should not be able to hide anywhere. You know, they should have to confront it, and that's kind of.
Thank you, Betsy.
Thanks for
and
asking the
Dr.
question.
Ram.
It's really great one.
Thank you, Ram. Great talk.
We have 2 text questions, but if anyone wants to verbally ask, you can go ahead and raise your hand. It's no problem. This is the first text question from Mike Evans. He asks, how good is the assumption that the unforced simulated variability equals internal variability of the climate system, for the conclusion that the unforced variability is a small part of the observed radiation imbalance? You could also,
Sandra, are you there?
Can you hear me?
Hello?
Hello? Oh no, did we lose him?
Hi, Cassandra, I can't hear you.
You can't hear me? Dr. Ram, oh no.
I can't hear you.
Test, oh no, what happens? Can
Ram,
everybody else hear me?
Ram, can you hear me? Because I can hear her. Ram, do you hear any of us?
We were having audio questions, or not audio issues at the beginning, so I wonder if this is, let me give him I'll give him the call-in number. Let's see. John, do you have his cell phone number?
Kelly, no.
Oh, what is this?
Maybe you can. Can you hear me?
Can you hear me?
I can hear you, Mike. I can hear everybody.
Yeah, so you could skip this question because I have to go.
Okay. Okay, sounds good. I'm sorry, Mike.
Yeah, I'm sorry, and thanks to for this talk.
Yeah. Here, I'm gonna ask him to call in.
We are coming up to the top of the hour.
Yeah, if it doesn't happen, it can't happen, but
This was an absolutely terrific presentation. He's always so good at this.
oh yeah, this was.
Yeah, I genuinely appreciate when someone tells me where their challenges are, where there's recently been progress made. And, you know, again, like a true scientist, there he was quoting lots of other people's papers and highlighting their importance. It's just, he's a great scientist and a great spokesperson.
He is, and thank you for coming, Betsy.
My pleasure. I'm just trying to make sure we make the most use of this time. The best thing we can do is, you know, talk about the content of this talk.
Hello?
Can you hear us?
Can you hear me?
We can hear you. Can you hear us? I guess not. We can give it. I mean, we're about done. I'm just hoping we could get another question or two to him. Oh, what a shame.
I look forward to seeing the recording of this later. This was such a dense, rich talk.
Oh yeah, it should be up, and this is for everyone. It should be up probably within the next day or so, and we can have that email to you too.
Yeah, terrific. Terrific.
I think we are not going to get him back.
Okay.
Okay, well, I'll just end it then. I'm so sorry, everybody, for the stunted Q&A section. Thank you, Dr. Ram, for this great talk. I'll email him afterwards and thank him. And thank you, everybody, for attending. Our seminar series continues next week. Please, everyone, make sure to come back. We got some good speakers to finish off the semester.